Hello everyone, welcome to this KANPUR-NPTEL online course on space environments and its effects on orbital spacecrafts. So, these days we are discussing the basics of plasma physics, and in this regard we have seen that is how the electric and magnetic field that influences the motion of the plasma particles. So, we have seen that is when we only considered the magnetic field, and we have seen that the trajectory of the charged particle is helical. And in this regard, we found what is the guiding center of the that is the movement of the particle in the helical path, then what is the pitch and pitch angle of the helical path. Then we have seen the diamagnetic properties of plasma. What we have seen, whenever there is the particle gyrates because of the effect of the magnetic field, because of the gyration it creates the moving charged particle creates the current in a direction which produces the magnetic field which opposes to the external magnetic field. So, this is called the diamagnetic or diamagnetism. So, you have seen that the plasma is basically it is a diamagnetic medium. Then we have seen the magnetic moment. Magnetic moment means when you multiply the current with the area, means area of that gyrating circle. Okay. Another phenomena we have seen, that is when we apply both the electric and magnetic field, then in that case the particle instead of its gyrating movement in a helical path, it also drifts. So, what we have seen, that is when you consider both E and H, then the velocity, the motion, we can represent it by three components. The first component is the parallel component of the velocity, and this is this represents a constant acceleration. Along the direction of the magnetic field, direction of E. Then the other component is the V E. So, this we call as the that is the uniform drift velocity. And which is perpendicular to both E and V. And we have seen that its expression is, we have derived that expression, B is it the cross product of E and B divided by B square. Okay. And the third component is VSC AC, that is the alternating component. So, this represents the gyration. With the tangential velocity of VSC T. Okay. Now, if we take the average of that is the velocity in one gyrating period, that is in one cyclotron in one gyrating period T, let us take the average value. Take the average value of V t, means if you take the average value of V t, then what you will find, since this tangential component of the velocity, or it is also the perpendicular component of the velocity, then perpendicular to the direction of the magnetic field. So, if the magnetic field in the z direction, then BAC will be in the x and y plane. So, what happens, this is represented by since the equation we have found that is the differential equation is the harmonic equations. So, we have found that the solution it is a circular function, either cosine or sine function. In that case, if I take the average value, this will be 0. So, in that case I can write this as NBE. What does it mean? That so this is the average value of the parallel component, and this is the vertical average value of the vertical component or perpendicular component. Okay. The other topic we have studied, that is the plasma oscillations as well as the plasma frequencies. So, what we have seen, that if there is any perturbation, local perturbation of this that is the orientation. Suppose if you displace the electron, we have seen that a column of electron who you are displacing, then there is a electric force or electric field will be developed there, because locally that becomes non-neutral. So, there will be an electromotive force or the E force, E field, and because of that, what is happening, because of that field, it will try to neutralize the particle, it will try to bring it back to its neutral position, but because of the motion of inertia, it will cross its neutral position, it will go beyond. Then a electric field will be produced in the opposite direction, will again try to bring it back. So, this way those electrons will move back and forth, giving rise to the oscillation, that is called the plasma oscillation. And we have seen that we are taking a one dimensional problem. This is given by the differential equation, it comes from the equation of motion. So, this is given by is equal to 0. So, this is again a harmonic equation. We can find that the x will be either a sine function or the cosine function, and here this omega p, this is called the plasma frequency. Plasma frequency, and we have derived this expression is equal to square root of this is the density of electrons per unit volume multiplied by its charge square divided by the permittivity epsilon 0, permittivity of free space multiplied by the mass of the electron. So, this represents the electron plasma frequency. Similarly, it can be for the proton also. In that case, you have to change the mass. So, basically the electron and proton, the frequency will be different, because so though the charge is be same or the number is same, but this because of there is a change in the mass. So, both will be different. And we have seen this plasma oscillation. This plasma oscillation is localized. We will see more, that is in the next session, that is the collective behavior of the plasma. So, in order to maintain that, the plasma is always neutral. Now, today we will continue with the same thing, but we will now take another topic, that is called the Debye shielding, or it is also called the screening effect. So, how we will do that? We will see that when we introduce an external charge into a neutral plasma environment, then what happens? Then there is a shielding, that is called the Debye shielding, and with respect to that we will find what is Debye length and Debye volume. So, let us consider that there is a there is a plasma environment, and so this there is arbitrarily this or randomly these particles are distributed. So, like that it can be a volume, and we can consider that is the number of the electrons per unit volume is equal to Ne, and since it is neutral. So, the number of the positive ion that should be equal, and that we will put at is equal to N 0. So, this is the condition initially. Now, we will assume that a positive point charge is brought and put inside this plasma environment. Let us consider that T 0 we bring some positive charge, that is we will consider it is a point charge, and then we will see now what happens. So, for that what we will consider? We will consider a coordinate system spherical coordinate system. This is x, this is y, this is z. So, this is the radius of the sphere. We will take this projection on this xy plane. So, this angle we will put at theta. This is the convention, putting the theta phi and r. So, this point will have the coordinate p r theta phi on this sphere. Okay. Now, we will assume that this charge is placed at the center of this is the positive charge I am putting here, positive charge q at the center of the sphere. Now, let us assume that the just at the initial condition, whenever we have imposed the charge inside the plasma. So, the number of that is n is equal to n I is equal to n 0 means it is neutral, there is no electric field, but since this has been introduced here, this will exert a force and it will or you know the potential energy, all these charges will feel a potential energy because of the introduction of this charge in the neutral medium. So, what will happen because of that, the potential energy or this phi r, that I can write it 1 by 4 pi epsilon 0 q by r. So, it will be, but now what will happen, since it is a positive charge, it will attract the negative charge. Negative charge means the electrons, and it will repel the positive charges, the positive ion. Okay. Now, another point to be kept here in mind, that is the positive ions are having the higher masses as compared to the electron mass. So, what will happen? This positive charge, it will attract the electrons around it. So, this process will continue, and after after some instances, this negative charge will it will produce again its potential energy. What it will do? It will now start repelling the negative charges. So, what does it mean? That now if any negative charge wants to come here, it will be repelled. The negative charge, it will be repelled, and it will attract the positive charges. Now, it is something like that, that is since the positive charge is having higher masses. So, their velocity will be much lesser. So, after some time there will be an equilibrium condition where no electron will be attracted or any positive charge towards it or positive ion, and surrounding this positive charge, now it has become, the area has become something like a non-neutral environment, and now assuming that the positive charges, they have the higher, or the ions are having the higher masses. So, they are the loss from this surroundings here to the to nearby that volume, it is negligible. So, what I can assume that near this charge there is a increase in the number of the negative charges. So, the charges, net charges, here I can write the net charges, the net negative charges or the net charges, I should know the net charges surrounding the test charge plus q. I can write it as is equal to q e n e minus n I, and as I said I can write this as q n e minus n 0. I can write in because what I am saying, because the number of the positive ions I can assume that it is that number has not decreased to that extent. I can assume that it is the initial value is the same. So, that is why I put it as n 0. Okay. So, now since this volume it has become now a non-neutral medium. So, I can apply the in this volume I can apply the Poisson's equation. So, what is Poisson's equation? Poisson's equation is del square phi r, this is equal to minus rho by epsilon 0, and now this I can write as minus q e by epsilon 0 n e minus n 0, or I can even write it minus q e epsilon 0 n 0 n e by n 0 minus 1. Okay. Now, we can show that we will not derive it, we can show that at equilibrium temperature T of the plasma, the particle density NER can be represented by n 0 e to the power minus q phi r divided by k b into T, where k b is Boltzmann's constant, which is equal to 1.38 into 10 to the power minus 23 joule per Kelvin, and T is the absolute temperature. T is the absolute So, now if I substitute this in the Poisson's equation, so I should be able to write the Poisson's equation. The Poisson's equations So, Poisson's equation will be del square phi is equal to minus q e n 0 divided by epsilon 0 n e by n 0 minus 1, and which I can write as minus q e n 0 divided by epsilon 0. Then I will substitute from this equation n e by n 0. So, that will be equal to n 0 no, n0 already I have taken here. So, n0 will not be there. So, it will be exponential e to the power q phi r by k b into t minus 1. So, now we have considered a spherical coordinate system. So, I am to write the Laplacian in spherical coordinate system. So, if I do that, so I can write this del square phi is equal to 1 by r square, then del of del r, then r square this is the r component, then next will be the theta component. So, theta component I can write plus 1 by r square sin theta, then del theta inside bracket sin theta delta phi by delta theta, then the last, that is the phi component will be 1 by r square, then sin square theta then del square of phi by del square small phi. So, this phi is r theta phi and this phi is the potential function. Okay. So, this will be equal to, minus q e n e by epsilon 0, then inside the bracket that exponential minus q e phi r divided by k b into t minus 1. Okay. Now, we have considered a point charge, and point charge we have placed at the center of the spherical system. So, we can consider this whatever this the charge volume or this field, this is symmetrical. So, what does it mean that this is that's only we will consider only the radial component. This other two components theta and phi component we can assume this to be 0, this to be 0. So, now so these two terms are 0. So, now I can write this equation will become 1 by r square del by del r square del phi by del r, this is equal to minus q e n e epsilon 0 and then k b into t minus 1. Now, this is a nonlinear, this equation is nonlinear. So, this is a nonlinear equation, and it cannot be solved, by an analytical method. So, only means you can solve it by numerical method. But we can take for some special cases or some approximate cases where we can simplify this equation and we can make this equation so that I can get a analytical solution of this equation. So, let us consider this perturbing electrostatic field. This is the perturbing perturbing electrostatic field phi r, it is very less as compared to the thermal energy, that is the kV into T. So, if you take this approximation, then this exponential term, that is e to the power q e into phi r. So, this is q e phi r, this q into phi r divided by k b into T. So, I can express, so I can write it something like, so this I can write as x, so it is known as x if I write. So, I can expand it, and all those terms. So, now this value has become very small. So, in that case what I can do, I can take only these two terms. So, in that case my this equation on if I retain only the first term, that is 1 and there, then my this equation will become the differential equation 1 by r square, then del by del r. In fact, I can write it now the total differential also by del r. This is equal to, I can write it and 0, then q e square divided by epsilon 0 k b into T phi r, where, or I can write this as equal to 1 by lambda d square phi r. This term lambda d is called the Debye length or Debye radius, Debye length or Debye radius, length or radius. So, I can write the solution of this equation. So, what is lambda d actually before I write the solution? So, lambda d is basically it is epsilon 0 k b T e and 0 q e square. And you can if you do the dimension analysis, you can show the lambda d comes in terms of length. Okay. And the solution of this equation will become phi r is equal to 1 by 4 pi epsilon 0 q by r, then e to the power minus r by lambda d. Now, you see the case when r is very small, r tends to 0. So, this phi r it will tend to 1 by 4 pi epsilon 0. So, similar to what is in the this isolated charge in free space, but when this r is very large as compared to this lambda d, this phi r will be tending 0. So, what you can assume that now that across that or about that positive charge there is a shield above outside which if the lambda if you go far away from this the point charge where this r is large compared to this lambda d, then we can have. So, there the outside is neutral. So, this is called the Debye shielding, Debye shielding, and at r is equal to lambda d, you can see that the potential it will reduce by 36.7% more than apart from this, that is if you do. So, it will be 36.7 divided by that the lambda d. So, this much potential will reduce divided by the lambda d. So, all this is about the this shielding, how this plasma that redistribute itself, so that they can retain the quasi-neutrality. So, with this I will complete it here, and then we will see the next topic, like what is the, we will summarize the different behaviors whatever we have studied till now. So, thank you very much.